So looking at the classifications of matter, the two major branches are the pure substances and the mixtures. And we can further break down pure substances into elements and compounds, and mixtures into homogeneous mixtures and heterogeneous mixtures. This video is mainly going to focus on the pure substances and the various categories of those substances that we are going to work with in this course. So in terms of elements and compounds, elements are the simplest forms of matter. There are currently 118 different elements. That means there are 118 different kinds of atoms. So there are only 118 different elements, but from those elements we can undergo chemical bonding. We can bond different elements together in different combinations, and we can make basically limitless numbers of compounds. And that's the world around us is obviously full of thousands and millions of different substances, and many of those are the chemical compounds when we combine the different elements. The elements are listed on the periodic table using their chemical symbols, and we'll get into some of the different categories as we talk through this video. And allotropes are a minor term that we mentioned in class. So compounds. So if we have elements as our basic building blocks of matter, then when we chemically combine or chemically bond elements together, we get compounds. And when something undergoes a chemical change or a chemical bond with another element, that means that they're really interacting down on the subatomic level, usually involving their electrons. And when they do that, it actually turns them into a completely new substance with a completely new set of properties. So hydrogen is an explosive gas, oxygen is a gas that supports burning or combustion, and when they react together and they explode, they produce water, which is obviously a liquid that we use to put out most fires. So the properties are quite different for each of those substances. So when hydrogen and oxygen bond together and become water, they cease to act like hydrogen and oxygen. They now act like something new, which is water. Same holds true for sodium reacting with chlorine to produce sodium chloride table salt. But elements can combine in lots of different ratios. So just because water is the most sort of familiar ratio of hydrogen and oxygen in a compound, there are others like H2O2, which is hydrogen peroxide, and having a different ratio means that you have a different compound with a different set of properties. Now, as we go through and talk about these different types of substances, we're going to use terms for their smallest piece, the particles of matter. So atoms are single particles, always single particles, like those listed up here. So they're always a single particle of an element, and they still have the properties of that element. Molecules, on the other hand, are when you have at least two or more atoms that are chemically bonded together. Now, you can have molecules for elements and you can have molecules for compounds. So H2, two hydrogen atoms bond together and they form one distinct unit, and that's called a hydrogen molecule. And if you break that bond apart, then you would get two hydrogen atoms. So the distinction is that when they're in the molecule, they're chemically bonded together. Up here we see a rendering of a water molecule where two hydrogen atoms have been bonded onto one oxygen atom. Okay, so molecules is a term that applies to when you have multi-atom particles that have formed through chemical bonds, and specifically covalent bonds, which we'll talk about again. So a molecule is like a unit made of multiple atoms, but not sort of an endless network of atoms. So it has to be sort of a given kind of manageable size number of atoms put together through bonding. We're also going to talk about ions. Ions are basically atoms that have picked up a charge, either positive or negative, through the loss and gain of electrons. Positive ions can be called cations, and negative ions can be called anions. And these are typically, as you would probably guess at this point, are involved with ionic compounds, are composed of ions down at the atomic level. Mixtures is we take those elements, we take those compounds, and we just put them near each other. We physically put them together. That's a key term for mixture. It's not chemically bonding, it's just physically mixing. So heterogeneous ones where there's just non-uniform composition, and then homogeneous ones like solutions when they're mixed down at the atomic level. So they look uniform, they look like one substance, and they sort of act like one substance, but in fact they're many different types of particles all mixed evenly together. And we'll talk more about those later in the course. So in formulas to distinguish between when things are bonded and when they're not, we use different conventions in chemistry. So one thing is that with elements, there's never going to be two capital letters in a row for the same element. So cobalt metal has the symbol CO, but the first letter is capital and the second letter is lowercase. And that's different than if you see C capital and O capital, because that means you have two elements. You have the element carbon, and you have the element oxygen. And I can tell that because of the two capital letters, I know that I have two different chemical symbols. So that's one thing to look out for, whether or not the letters are capital or small. The other thing to look out for are subscripts and superscripts. So subscripts are little numbers that are below the formulas, below chemical symbols, and they indicate bonding. So in the below formulas, O2, the way it's written on the right, this 2 implies bonding. And that tells you that you have two O atoms bonded together. Whereas on the right, because there's no 2 down here, there's only a 2 in front, this tells me I have two separate oxygen atoms. So distinctions of a superscript versus when the number's in front, it's called a coefficient. The other type of number you'll see is something called a superscript, and it's used to denote ion charge. So 3 plus means a +3 charge. A minus symbol means a 1 minus charge. The number comes first, so the 3 comes before the plus. Okay, moving on quickly. Now, we can take elements and we can take compounds and we can further subdivide those types of matter. There's kind of 4 categories that the IB is going to be concerned with. Those are metallic, covalent, molecular, giant covalent, and ionic. So you should be able to sort of predict, given a chemical formula or given the types of elements, you should be able to figure out what type of bonding and structure it will have, and you should have some sense of the major properties for that type of substance. So if something is metallic, you should know that it's going to be a conductor of electricity and that it will be malleable, that you can shape it. Whereas if something is ionic, you should know that it will be very hard and brittle, have a high melting point, but that it's not malleable, that it will crack if you push on it, and it will only conduct if you melt it and make it molten, things like that. So how will we know? How will we know? Well, the first one is probably the most obvious. We talked about one major category of elements are the metals, all these ones in blue over here. These are all metal elements, and metals bond to their atoms through metallic bonding. And that's a fairly obvious and solid name choice by the chemistry community, nice and easy, okay? And the theory of how metals bond is that when these atoms get together, all these metal atoms, what it means to be a metal atom is that you have a fairly loose attraction for your own electrons. And so those electrons actually become, the outer electrons of metal atoms become free to move around the structure. And there's a term for that. It's called being delocalized. They don't have one location. They can be in any location around the structure. So if you think about a metal, if you can zoom in on any piece of metal, what you would really see is sort of a giant mass of somewhat, there would be a regular geometric arrangement of the particles, but there'd be, and we're thinking of an element here. So all the atoms are the same. You can see here they're all purple. So that's representing that they're all part of the same element. So same types of atoms. It's a large sort of lattice of atoms, or technically they are ions because the other electrons are moving around, so the remaining particles are positively charged, so we say the metal ions, and they have the delocalized electrons moving around them. Because the electrons are free to move around, it allows metals to be good conductors of electricity. And because of those delocalized electrons flowing between the ions, when you push on the ions, they actually can change position while maintaining their bonds, while maintaining their attractions. And that's quite unique to metals, and it allows them to be shaped. And those are really the most important two properties to try to remember about metals. Their melting points can be quite variable, so there's not one thing that you need to remember about their melting points. If we go on to covalent and we go into nonmetals, so when nonmetal elements being these ones in yellow, and to a certain extent the metalloid elements that are listed here in red, particularly silicon is what matters for us, these elements, when they bond together, they're going to bond through something called covalent bonding, where electrons are shared in pairs between specific atoms. So two atoms share electron pairs with each other. So it's very different than the metallic bond where the electrons can kind of go everywhere. In the covalent bond, the electrons can only go between two atoms. So in a hydrogen molecule, there's a pair of electrons between the two hydrogen atoms, and the electrons can only go around those two hydrogen atoms. They can't go anywhere else. So it's very specific. Okay. Now, although a couple of non-metal elements, like the noble gases, the elements over here in the far right column, they exist as sort of single atoms. And they're all gases, so if you have a helium balloon, it's full of little helium atoms that are unbonded, not actually bonded to any other atoms, just single atoms of helium bouncing around in that balloon. But that's pretty rare that things actually exist as lone atoms. Most of the time, the nonmetal elements exist as little molecules. So like hydrogen molecules and oxygen molecules, O2, H2. Even phosphorus and sulfur exist in these cool combinations of 4 phosphorus atoms and 8 sulfur atoms. There are 7 elements that you're expected to know exist as small diatomic molecules. They are arranged conveniently in the periodic table more or less near each other. So they are H2 over here on the left, and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And we'll spend some time trying to practice remembering those. Out of the nonmetal elements or metalloid elements, there are a couple that you're expected to know don't exist as molecules like most nonmetal elements would, and instead, when they bond together covalently, they don't make little small particles, molecules, they make giant networks. So the classic examples are diamond and graphite, which are 2 different forms of carbon, but they're both examples of giant structures. And the graphite and the diamond, both of these would continue on in all directions. So in one diamond, you're talking about millions and billions of carbon atoms that are all bonded to all their neighboring carbons, and then those are bonded to all their neighboring carbons. And so it's this giant network. And because of all those covalent bonds between all of the atoms, they end up being extremely hard, extremely high melting points. So it's basically the strongest type of bonding, or at least that's kind of the general principle to take away. That a giant covalent structure is extremely strong, as opposed to molecules, which, although a molecule is held together fairly strongly itself, molecules are not held to their neighboring molecules very strongly. So if I have a hydrogen molecule, is fairly strong and held together fairly tightly by that covalent bond, but the attractions in between hydrogen molecules are very weak. These are called intermolecular forces. And that means that most gases most liquids that you've ever been familiar with, those tend to be molecular substances. And some solids, of course, are also molecular, but they tend to have relatively low like melting points and boiling points, unlike the giant covalents and the metals and the ionic compounds. There are, of course, compounds that bond together covalently as well. So when non-metal elements, different non-metal elements bond together covalently, they form compounds. And most of them form molecules. So some examples here, like water, carbon dioxide, and glucose, are all famous covalent molecules holding non-metal atoms together through covalent bonds, but forming these little distinct units, these small particles of a couple of atoms, water molecules, CO2 molecules, and glucose molecules. There is also one example you're expected to know of a compound that has a giant covalent structure, and that is SiO2, or silicon dioxide. So you can see it looks a bit like diamond, except it has different types of atoms in it. And so when we think about how are these different types of compounds represented, well, I can tell that these are compounds when I look at these pictures because they have different types of atoms connected together. And I can tell the ones on the left are molecules because they're just a couple of atoms forming these sort of distinct new particles. So those look like molecules, so they're probably covalent molecules. The one on the right, you have lots and lots of atoms all connected with these lines. And the line is generally the way that we represent covalent bonds. You have this sort of interesting geometry where it's not really just looking like a cube or very cubic. It kind of has funny angles to it. So those are typically traits of covalent compounds, things that we models of covalent compounds. So those are the types of things you're looking for if you're given a picture to try to decipher these things. So I've already mentioned a few of the properties, so I'm going to try to hurry myself up and get on to the last type of compound, and that's ionic compounds. So we've talked about metals and metallic bonding. When we have nonmetals, we do covalent bonding, whether it's a nonmetal to itself or different nonmetals together, they all do covalent bonding. And then as a general rule, when nonmetals and metals bond together, they bond through what are called ionic bonds. And that's because electrons actually get transferred from one atom to another. So like a metal atom will lose an electron over to a nonmetal, and that will turn them into ions. It will turn them into things with charges. So you get a Cl minus ion, and you get an Na plus ion. And once you have opposite charges, opposites attract. That's a general rule of electric charge. The thing about ions, though, is they don't form distinct little molecules of just a couple of ions. Whenever ions get together, it looks a bit kind of like how the metal got together, where you have this giant network, this giant lattice of ions. And we actually call this a crystal lattice, is the term for this kind of structure. But unlike the metal, at least how you'll see it represented, for metals, most of the time we're going to be talking about pure metals, so pure elements like iron or copper or something like that. So all the atoms look the same, whereas clearly this is different. In this crystal lattice, you can tell that there's two types of elements. And because I can see that there's two types of elements, I know that this is a compound. And because they're kind of alternating one after the other, that is a pretty clear-cut sign that we're dealing with an ionic compound where the opposite charges have to alternate, because opposites attract and like charges repel. So you'll never see two of the same next to each other when you have an ionic compound. So you can see that like this green one is completely surrounded on all sides by positively charged purple ions. And so that's a clear-cut sign of a crystal lattice ionic compound. Sometimes you see it like this, and there are some sort of dotted lines, so you might confuse that with covalent, but again, they've indicated some charge. It's also very, very cubic. These like 90-degree angles in all directions. There aren't too many examples in covalent that you'll see like that. So these large crystals at 90-degree angles is sort of the classic way to present ionic compounds. So in this one, we have the sort of crystal lattice structure that's very rigid. all those positives and negatives have to stay in that one spot. They can't slide around or they'll break apart. So they're very hard, high melting points. And these compounds are neutral overall, but they're full of these charged ions. So they don't conduct when they're solid because all the ions are fixed in place and they can't move. But if you melt an ionic compound, and at that point we call it molten ionic compounds, then the ions can move, and if these charged ions can move, then we get something that can conduct electricity. So there are different types of compounds. I hit you with a lot there. Okay, we've hit you with a lot so far this year. There are a lot of different types of compounds: metallic, ionic, and then different categories of covalent. As our general overview, we've got metals for metallic, metals and nonmetals for ionic, and then we have nonmetals for giant covalent and covalent molecular. The metallic structure is all those metal atoms in a large sort of lattice together with the delocalized electrons all around them. Ionic is the alternating large structure, very cubic, very regular, from those oppositely charged ions that need to alternate. The giant covalent is more of this, we call this a tetrahedral shape, but we see the atoms and they're connected with these lines, and that kind of networks out in all directions. So it's a large network of atoms all covalently bonded, whereas the molecules are little distinct particles made of multiple atoms like this, but they form little distinct units. They have an end. They don't go on in these large networks like the top three do.